Good afternoon, ladies and gentlemen, Conaplin committees, and hello to all Conaplin participants. I'm here today to present my paper entitled The Experiment on a Transformer Model Indonesia to Sundanese Neural Machine Translation with Sundanese Speech Level Evaluation. But before we start, allow me to introduce myself. My name is Restu Primandhika from Universitas Pendidikan Indonesia, and this experiment was also done with Mr. Muhammad Nadzeri Munawar from GTP Labs and Mr. Aceng Syaifullah from Universitas Pendidikan Indonesia as well. So in this occasion, allow me to bring the topic related to translation in natural language processing that is related to Sundanese language. So let me begin the presentation. So first, this may raise a question. Why we're doing this experiment while there is some other translation machine, like Google Translate, for example? Okay, there are some main grounds which came to this research. First, dealing with the context problem in machine translation. It's a general problem for machine translation since word sense disambiguation or WSD becomes the open problem in computational linguistics. And in this case, we started with its evaluation. As also said by Lobby in 2018, with the rapid progress of a neural machine translation, or later we call it NMT, translation mistakes and inconsistency due to the lack of extra-sentential context are becoming more and more noticeable among otherwise adequate translations produced by standard context-agnostic NMT system. So there are terms context-agnostic for machine translation that translates in general without noticing the context. Okay, secondly, neural machine translation as a new approach. Okay, back in early 90s to 2016, okay, it's such a long time for a statistical machine translation become the standard in machine translation industry. But neural machine translation becomes the trend in only 2 years and has been adopted by Google and Microsoft as a proof. So, although this time we're still trying to find the best model for neural machine translation that is context aware. So in Sundanese, we have this kind of problem too. Okay, the problem of speech level, as said by Aji Prosidi, bahasa Sunda anu pinuku undak usuk jadi panghalang sabagian urang Sunda anu rek nyarita atawa nulis dina bahasa Sunda. Boh sieun salah ngagunakeun atawa sieun disalahkeun. Okay. So this is ironic when Sundanese people itself had a constraint, to speak their own language because of speech level. So in this case, we also believe that machine translation could be a solution for Sundanese language sustainability. And it is supported by Suryani's statement, Sundanese translation into Indonesian is important. And vice versa, I think, considering the Sundanese language speakers getting reduced significantly each year. So this experiment is also an initial project of Indonesian to Sundanese machine translation optimization to continue the few former researchers. Accordingly, the research aims that we want to achieve in these experiments are conducting the test on the best model in neural machine translation to overcome context problem. Secondly, measuring the transformer model capability for generating contextual translation result. And third, evaluating Sundanese speech level problems in translation. And in addition, we're going to find the correlation between training data and translation result. This experiment started with building Indonesian Sundanese parallel corpus. We built parallel datasets for our NMT experiments. So the parallel corpus itself is a large amount of human translated Indonesian to Sundanese text or vice versa that are used for machine translation learning. Yeah, we've collected the text from the internet using self-built script since there's no open parallel corpus for Indonesian and Sundanese, or there is no toolkit as well. And then we move to the pre-processing the text. Okay, pre-processing in this case, we've cleaned both language texts from noises such as abbreviations, inconsistencies of writings, typos, and etc. Okay. For example, the word YG, okay, the word YG in Indonesia, YG should be written yang or Y-A-N-G, Y-A-N-G, yeah, or acute E like this, E curug in bahasa Sunda. For example, word HD should be written HD with E curug, okay, that sounds phonologically E. Okay, and then we split the data for training and test and then validate it. Okay, then the core process of this training on NMT, this is the core process. As we know in AI, machine needs to learn how to translate one language to another. Okay, this process took about quite a long time, in this case 4 days. Yeah, this training generates a language model that we can equalize this with having the brain of our NMT. Okay, then we've done a test with 2000 pair of sentences as a sample of this experiment. And then the last step is to evaluate the translation score using BLEU, which later we'll see what it is, and find the best translated Sundanese sentence to be evaluated regarding to social context. Yeah.
The ultimate goal of any neural machine translation model is to take a sentence in one language as input and return that sentence translated into a different language as output. For example, in this case, we try to translating from English to Spanish. At the most basic level, the encoder portion of the model takes a sentence in the input language and creates a thought vector from this sentence. This thought vector stores the meaning of the sentence and subsequently pass to a decoder which outputs translation of the sentence in the output language. In this architecture, the encoder and decoder are both recurrent neural network, or RNN. At the basic level, RNNs are neural networks designed specifically to deal with textual data. Let me drill down the case of encoder. Each word in the input sentence is fed separately into the model in a number of consecutive time steps. At each time steps, the model updates a hidden vector using information from the word inputted to the model at the time step. This hidden vector works to store information about the inputted sentence. At each time steps, this hidden vector takes in information from the inputted word at the time step while preserving the information it has already stored from the previous time steps. Thus, at the final step, the meaning of the whole input sentence is stored in the hidden vector. This hidden vector at the final time step is the thought vector in which is the inputted into the decoder. Let me drill down the case of decoder. Rather than just proceeding to the next time step, the decoder will use an additional weight matrix to create a probability over all of the words in the output. In this way, the word with the highest probability in the output will become the first word in the predicted output. In this case of the decoder, we try to translating from "the cat likes to eat pizza" to "El gato le gusta comer pizza." Okay, let's begin to translating. The word "el" was given the highest probability to the first word for output prediction, and we proceed using "el" as the input in the next time step. For the next word, the word gato was given the highest probability. We proceed this way through the duration of sentence until, for example, we run into an error into the word after gusta. As you can see, the decoder has predicted pizza to the next word in the translated sentence when it should be actually comer. During the training process, we are going to keep pizza as predicted output, but force our decoder to input the correct word comer as the input for the next time step. This is a strategy referred to transformer model and helps speed up the training process. All of process of neural machine translation, we use open source called OpenNMT library that have been developed by researchers from Harvard University. One of the challenges of building machine translation system is how to evaluating quality of machine translation. BLEU is popular method to measure quality of machine translation system. BLEU stands for Bilingual Evaluation Understudy. is a metric for automatically evaluating machine-translated text. The blue score is a number of percentage between 0 and 100 that measures the similarity of machine-translated text to a set of high-quality reference translations. As seen on the table, the greater of blue score indicates the higher of translation quality. Blue compares the n-gram of translation with n-gram of reference translation to count number of match. The more number of matches between machine and human translation, the better is quality of machine translation. Pn indicates how to calculate n-gram. Count clip means number recurrence of reference compared to machine translated based on number of gram. By default, blue use until 4 gram. BP stands for brevity penalty. Will be 1 if translated text is greater or equal than reference text. The closest reference sentence length is the best match length. With the brevity penalty, we see that a high-scoring translation will match the reference translations in length, in word choice, and word order. And finally, blue score. This comes from brevity penalty and n-gram calculation. This is the example of how to calculate blue score. For simplicity, we just use until 2 gram or biogram to calculate blue score, and just use one reference of human translated sentence. Because in real case, blue score use until 4 gram, and for better accuracy, usually use more than one reference of human translated sentence. In this example of left side, there is source of sentence in Indonesia, reference of human translated sentence in Sundanese, and machine translated sentence in Sundanese that will be calculate blue score. On the right side, there is a table that indicate calculation of 1 gram or unigram and 2 gram or biogram. The first, let we see on calculation of unigram. In unigram, we map each word of machine translated sentence as seen on ref column. Anjeun teu cocok sareng anake is one word map from machine translated sentence. The count column indicates number of occurrence in machine translated sentence based on ref column. For example, word anjeun just occur once in machine translated sentence. The word teu just occur one in machine translated sentence, and so on. The count clip column indicates number of occurrence in human translated sentence based on ref column. For example, the word anjeun has no occurrence in human translated sentence because use word hidup instead of anjeun. The word teu occur once in human translated sentence, and so on. The second, let we see calculation of biogram. In biogram, we map each 2 words of machine translated sentence as seen on ref column. The calculation same as unigram that we calculate number of occurrence in translated sentence based on ref column. The result could be seen on the table. After mapping the number of occurrence, we can calculate score of P1 and P2. 5 indicates the sum of count clip 1, 2, 3, 4, 5. And 7 indicates sum of count 1, 2, 3, 4, 5, 6, 7. And for P2, 3 indicates sum of count clip 1, 2, 3. And 6 indicate sum of count 1, 2, 3, 4, 5, 6. After got P1 and P2, we can calculate the final of blue score. based on formula that I've just explained in the previous slide. The result of blue score here is 80.25%. This result has good quality because we just use 2 gram. The blue score result should be lower if we use default blue calculation using 4 gram.
So here, I'm going to give a little explanation about Sundanese speech level or undak usuk bahasa. Using formality distinction in Sundanese language is essential. Yeah? The choice of words determine what speech level and is socially didactic. Okay, this is in accordance with what Levin portrays in social didactics. That is the predetermination of social differences that are according to participant roles, mainly aspects of the social correlation that is possessed between the speaker and addresses, or a speaker and some reference. Hence, speakers are always making choice of what level of formality to use depending on social context. Okay, according to Taufik Fatur Rahman, undak usuk or tata krama bahasa Sunda divided into 3 stages that are bahasa loma, bahasa loma, bahasa sedang, and bahasa lemas. We use bahasa loma when speaking with friends. Okay, speaking with friends of equal or lower social status. When speaking to family, superiors, strangers, or our older individual, we use bahasa sedang or bahasa lemas. Okay, in this case, self-honorific, bahasa sedang. Giving honorifics to others need to be distinguished, cannot be replaced in use. Okay, so in Sundanese, doing the conversation by noticing social context means paying attention to undak usuk. According to Kamus Umum Bahasa Sunda or LBBS, undak usuk means the speech level that is related to politeness. One that uses Sundanese language in conversation without using the undak usuk can be labeled as impolite. Based on the definition, Sundanese speech level plays an important role in daily conversation to show honorifics and to value one another in society. So machine translation had to follow this concept as well. When translating from Indonesian into Sundanese, a translator must determine one level of formality or another. However, to enhance the quality, there are still some problems. The first here is low resources parallel corpus data available on the internet for training data. Okay, to achieve human quality translation, the machine needs huge amount of parallel text for its training. This issue also happened to former researchers that published their paper on machine translation in Indonesian vernaculars. To overcome context problem, actually 100,000 or even million is needed. So with limited amount of parallel, we try to only evaluating. Okay, secondly, as Google Translate also adapted neural machine translation as their basis, and Google use English as a medium that causes the translation result has a syntax issue. Okay, this is what distinguishes from our model from Google's. We train directly with Indonesia to Sundanese corpus. So continuing from the translation problems in NMT, we collect sample data here from the result of our NMT. This is the most frequent issues in our NMT when two-fold distinction is quite problematic in context. Okay, ideally the result should be the same, but in NMT the result follows what is in training data, which is dominantly comes from formal language, or in this case bahasa loma. So for aku minta maaf in bahasa Indonesia, when it is translated through our NMT, it says urang minta dihampura instead of simkuring minta dihapunten. But we also find the other bias when bahasa loma converted into bahasa sedang. The word hidap here, the word hidap here has low probability to be appeared in NMT. So as a replacement, the NMT translate the word cow, this one, this one cow in Indonesia to anjen. Okay, anjen has more probability than hidap, but this kind of case in how translation has low percentage. Okay, this one, Lost in our findings because of small datasets, we certainly also have problem with the adequacy of translation. In the first example, we find that the translation result is completely out of meaning, and there is no related word at all. Okay, mahal banget sih harganya, Mang. In Indonesia, semantically implies that something is too expensive. On the contrary, the result sounds meniraos tuanganana, that implies the food is very delicious, so there is no correlation at all. And the second case, we also found that the most of complex sentences has insufficient word to translate, or in the machine translation, this phenomenon called OOV, or out of vocabulary. OOV in the second example can be seen in the word ang, this one, in the brackets. That means word masna has no equivalent diction in our NMT vocabulary, and this is one of the example. Different from the first one, our NMT did translate on most word correctly, so except on word dibleh, dibleh, this one, mean be cut. Meanwhile, in the result shows dikencarkan or to be released. From our discussion, here is the summary. By conducting the test on the best model in neural machine translation to overcome context problem, we found that transformer model in NMT is still lacking for context-aware machine translation. But it is the best model to overcome syntactic problem. This is based on our comparison on other two models that was in candidate, that outwon attention and small NMT model. This is shown by 42% of blue score. Okay, using transformer model for syntactic problem is good, but for complex sentences, it has a large number of out of vocabulary or OOV, as we discussed before. And for the speech level, Bahasa Loma had 56% of whole vocabulary. That we demand the available of parallel corpus in the internet to do more experiment on MT or machine translation and overcome the synchronous context problem. And so that's all from our presentation. Thank you.